Hi everyone, this is Mr. Carlson. I'm just trying to help you guys figure out this last CFA that you've gone through. Let's take a look at the problems and see if we can reason our way through the responses here. Okay, so we have here a heating curve. Let's go ahead and write that up here. Okay, and on a heating curve, there's multiple segments. Each of these segments represents something different about this substance as it undergoes changes. Okay, where we have these horizontal lines, this is where phase changes occur. So to do question number 1, where you're asked to identify the melting point, the condensation point, the freezing point, and the boiling point, you just need to look at these two horizontal lines. Okay, if you remember to our lab, the freezing point and melting point actually occur at the exact same temperature. And since this is a heating curve, we are going to go with this lower value here. So at negative 60 degrees, that's where the melting point should occur. But it's also where the freezing point occurs as well. Okay. Let's go up to this second horizontal line. Another phase change occurs here. Okay. As we transition from a liquid to a gas, we undergo the boiling point, and this occurs at positive 60 degrees Celsius. The condensation point is at the exact same temperature as the boiling point, and the reason for this is all about the energy flow. When energy goes into a system, right, it would boil at this temperature. If energy is leaving the system, it would condense at this temperature. So let's get those last values in there. All right, so let's mark these values on here and determine the state of matter at each of the following temperatures. Okay, at 20 degrees Celsius, so let's read our graph. That's right here. This is on the portion of the line that represents a liquid. So we know that we have a liquid at 20 degrees Celsius. At negative 60 degrees Celsius, this phase change, there are two states of matter present, and they are in equilibrium with each other. So we have both a liquid and a solid. Both of those are present here. At negative 100 degrees Celsius, here on the graph, this indicates just solid. Note that when you have a sloped line, you can only have one phase of matter present. All right, let's go up to 80 degrees Celsius. So that's halfway between 100 and 60. So that's right here on the line. It would appear we just have a gas present. And finally, at 60 degrees Celsius, which is here on this line, we should have both liquid and gas present in equilibrium with each other. All right, let's move on to our next slide. Here you have two particle models that we needed to analyze. In Model A, assume an exothermic change is occurring. What type of phase change is represented by the model? Then you need to justify your answer. Okay, so we see a bunch of particles here at the bottom. Okay, they do not seem to be in any organized fashion. So this is reminiscent of what we know from our particle models previously as a liquid. They're close together, they're dense, but the particles are not organized in a fixed arrangement. Up here, clearly particles are spread out, and they enter into the volume up above the liquid below. So we have a liquid and a gas here. All right, since this is an exothermic change, this means that energy will be leaving the system. As energy leaves a gas, it's going to condense. So we now know that we have condensation occurring at this level. All right, so justify our answer. Okay, so once again, let's go back to the picture. Okay, when an exothermic change occurs, energy is leaving the system. Let me write that up real quick here. Okay, the gas changes to liquid. Okay, also known as condensation. All right, sorry, you have to apologize for my handwriting here. So let's go on and look at this second one here. It would appear similar to A. There are some disorganized particles here at the bottom of our container. Those are also liquid. Okay, but these particles here are much more arranged more closely. This represents a solid. But since we are undergoing an endothermic change, energy is going into the system, and the solid particles are going to get more agitated, and as they get more agitated, they are going to separate from each other, transitioning into the liquid state. So when we go from solid to liquid state, we are going to have the melting occur here. So this is also known as fusion. So let's go ahead and justify our answer here. This one would be similar to what we did on the last one. Right? When an endothermic change occurs, so let's get our language right here. I keep misspelling things here. All right. When an endothermic change occurs, energy enters a system or is absorbed by the system. Right? The solid changes to a liquid. Also known as melting. All right, that's question 3. Let's go on to the next question. Question 4. Okay, this is relatively new concept for us, but we can figure this part out fairly easily. Analyze the phase diagram below for carbon dioxide. What state of matter do you predict at a pressure of 0.3 megapascals and a temperature of negative 50 degrees Celsius? So let's just go ahead and mark where that we think that might be on our graph. So going to 0.3 megapascals, we go over to where we believe negative 50 degrees Celsius is. So right here. As a result, okay, we are going to surmise that this should be a gas under these pressure and temperature conditions. Okay. Now let's go to the second part here. At a pressure of 4 megapascals, at what temperature does melting occur? So we start here on the x-axis and we work our way over until the solid changes to a liquid. So that's here. Okay, and then we want to extrapolate by going down, down, down. Sorry, I'm drawing a little dashed line here. It's a little hard to do on the computer. Okay, our prediction is this occurs at approximately negative 60 degrees Celsius. Okay, at what range of pressures is sublimation the only possible phase change? Okay, remember sublimation is when a solid transitions to a gas. That occurs along this entire line right here. I'm just going to circle this segment. Right? And we want to know what pressure that is. So I'm going to read over here to, sorry, I've got things in the way. I'm going to read over to our y-axis here. And it looks like at 0.5 megapascals and below, okay, we should have sublimation occur. So anywhere from 0.1 megapascals. 2.5 megapascals. Okay, MPa. That is the place where sublimation can occur. All right, let's move on to our next slide here. Okay, this is the last question from the CFA, and possibly the one that's most challenging for us to work through. So let's go ahead and do our calculations, determining the amount of heat lost or gained as we go from negative 20 degrees Celsius, right, to 100 degrees Celsius. Let's first mark those places here on our graph. So here is our starting point. We're starting at negative 20 degrees Celsius. I marked that with X. Okay, and our ending point is 100 degrees Celsius up here. Okay, as you can see, there are 3 segments for our heating curve that we need to analyze. The first segment is this diagonal line from our X up to the horizontal line. The second segment is this horizontal line, and the third segment is this additional diagonal line at the top here, where it's sloped positively. So let's break these down one by one. Let's look at equation number 1. Since we are undergoing a temperature change, we need to use this equation, Q equals mc delta T. And since this is the liquid phase, okay, we want to use the specific heat of the liquid, okay, in our calculations. So for part 1, Q equals the mass, which is 75.0 grams. Let me put that in parentheses, times the specific heat capacity of the liquid, which we have as 3.20 joules per gram degrees Celsius. Finally, delta T. Delta T is the final temperature for this segment, which is at 60 degrees, right, minus the initial temperature, which is negative 20 degrees. So let's do that here real quick. Delta T equals 60 degrees minus negative 20 degrees. Hey, we do that math, that is 80 degrees Celsius. All right, quick little check. Our units cancel out, grams go away, degrees Celsius go away, and we're left with joules. All right, let me pull my calculator up real quick. Sorry, give me a second. 75 times 3.2 times 80. Okay, and I get 19,200 joules for segment 1. All right, let's move on to segment 2. Okay, on segment 2, since we are not undergoing a temperature change, we can't use mc delta T here. Instead, we want to use this equation. Q equals the mass times delta H of vaporization. Get the right thing in there. Okay? So, since we're transitioning from a gas to a liquid, we want to use the heat of vaporization here. This one's a little bit easier calculation. So we know we still have 75 grams. And we're going to multiply that by the heat of vaporization, which was 1,250 joules per gram. Okay. Let's do that math really quick. 75 times 1,250. And I get 93,750 joules. All right, let's do step 3 now. This is the top line here. Okay, we can go back to using mc delta T. But this time our specific heat capacity is tied to the gas. All right, let's do our delta T calculation again here for the top part. We're going to end up at 100 degrees. That's our final temperature. minus the transition temperature, where it transitioned from liquid to gas, which was 60 degrees. So our delta T is 40 degrees. Okay, let's go ahead and plug in those numbers now. Right, our mass equals 75 grams. Oops, let me erase that real quick. Yes. All right, our mass equals 75 grams. Our specific heat capacity for the gas is 1.35 joules per gram degrees Celsius. Get that right here from our data set. And finally, our delta T is 40 degrees Celsius. Okay, let's multiply those three values by each other. 75 times 1.35 times 40. I get 4,050 joules. Right, to get the total heat, right, we just need to add the heat from those three different segments that we just calculated. So Q1 plus Q2 plus Q3. Maybe I should go back and label that. That's Q1, Q2, Q3. All right, so let's rewrite those numbers. We have 19,200 joules plus 93,750 joules plus the last one, 4,050 joules. Okay, when we add all those together, give me 1 second, 93750 and 4,050. Okay, I get a total of 117,000 joules. So this is our total, Q total equals 117,000 joules. All right, I hope you find this useful as you're going through this CFA. Come back and check any of these things out again to see if you need a refresher. Okay, I wish you the best of luck on your test. Make sure that you're spending time really solidifying your understanding of these principles. That's all. We'll talk to you guys later.